So this is slightly different from what you usually learn in your, for most of people that say, oh yeah, if we have a laser light try to induce a optical property of an emitter, usually we know if we just shine a laser light on it, then it will emit a light. If we use very little light to excite it, then it will emit very little light. Then if I double my excitation intensity, then the emitted light the intensity will also double, right? This is in the so-called linear regime, but then it will eventually saturate, then it will be flat. When you go up, then it will just stay right there. And that indeed, for most of the emitter, that's what you observe. But that is because you have decoherent process that happen extremely fast. And everything that I describe over there in this Bloch sphere and rotation, that's only assuming that it's all in the time scale much shorter than coherent time. Then that dynamics is described by this Bloch equation. So now, if we can do it within that time, operate in that time, so now we go and find out a state that has very long coherent time, then this is what it looked like. So in the laser pulse, the pulse width is fixed. So what we'll do is we just change the intensity. So within one pulse, and we integrate this omega t times this whole pulse width, then that angle is what we usually also call input pulse area in the coherent control. Now, if I quadruple my laser intensity, I double my input pulse area because it is electric field integration with respect to time, and intensity is electric field to the square. And then you will find out then if I now change my intensity, then when I change my intensity, then the laser intensity, then I am really scanning the angle. It's now go into theta, and theta is going to be a pi or 2 pi. Then I should expect to see the emission light come from this quantum dot. If I first increase my laser intensity, I should see it go brighter, brighter. Then I should see it go dimmer and dimmer. And that is what people call Rabi oscillation. Okay, so you probably heard this word Rabi oscillation, and it was observed in the atomic system back in 1973. And then, this is taking an atom, then you emit, and in theoretical input pulse area, it will show, if everything is ideally coherent, then you should see this sinusoid going on and on and on and on. And don't just so-called underestimate this achievement of observing the Rabi oscillation, because all coherent control, it really underlied all the coherent control and all the quantum operation in any kind of quantum algorithm. Okay, so that is the most basic operation. And then 30 years later, we have observed it too using a quantum dot. And there is a slight difference that I need to point out. In that old work, what they do is they use a laser to excite the state, but then they also look at the thing coming out, the same energy. And you will see a quantum dot that emitted, laser line come in each pulse contains tremendous amount of photon. And only a very small fraction of them ended up coming here in the act with this quantum dot. And then they emit the light. So the light intensity here compared to the laser intensity is probably billion or hundreds of billion to 1. Okay? How is it possible for one, to observe this under such a background? So in the old day, what they did was the lifetime here is very, very long. So what they ended up doing is laser pulse come in, and then when laser pulse comes in, during all those scatter time, they just don't look at it. They just shut off the detector. Then after that pulse complete, then they start open up the detector and look at what is the intensity coming out. And then they start doing that. And so that they can do this. Now, when you do it for a quantum dot, okay, it is very difficult to do that because this thing, its decay time, is of the order of nanosecond or shorter. And you just cannot find any kind of optical modulator that will operate it so fast. So you have no choice. You just, you know, so how do you then sort it out? So this is what we did. What we ended up is we picked this, the exciton vacuum and exciton excited state. We treat these two states as a two-level system. Then we drive it. So all the Rabi oscillation occurring is really on this two-level system. And what we do know that is, even though we pick those have a very long coherent time, about 50 picosecond, but the radiative lifetime here is about 1 nanosecond. So within 50 picosecond, they will drop down to this ground state, exciton ground state, emit the photon. So this intensity is the one we observe when we operate it. So if we have a pi pulse, we just ended up leave it right there, and then we let go. This external laser pulse is not driving it, and then we just let it drop to here, and then we look at the intensity. So if we drive it to the pi pulse, then when we look at the emission, that's when we see the highest intensity. Then if we then pull it out and then bring it down back to that, then we will see the lowest intensity. And that is exactly what we see. But you can see here, our quality factor is really not that high, right? That is because during the time of our operation, a lot of coherence are lost, okay? The whole thing is sinusoidal Rabi oscillation. Its quality factor is precisely determined by how much of the coherence that you have maintained. Okay, now. So this was the one that we published in PIL 2002, and it's probably also the one that been remembered by most people, all right? But really, in that paper, there is another feature, okay? And somehow people they just overlook it, and then later on kind of reproduce that part and call it kind of tomography. Of course, the quantum tomography is a little bit more than what we observed there. So I want to give you this, say, well, if you have two pulses, now come to do interference, you have known that in earlier that I say, oh, if you have a weak intensity, then you will just see this interference, quantum interference. From that, you can measure the so-called T2 time. And you will see sinusoidal thing. But if you increase the intensity, so this would be what you usually see, but when you increase the intensity, suddenly its periodicity changed. And that's when we say, we were doing this quantum interference before we stumbled upon this, that we realized we observed Rabi oscillation. And it was my student, Han Tun, met Professor Takagahara at the Kyoto Institute of Technology in a conference. And then he looked at that. He said, this may be Rabi flopping phenomena. So we thank him for that because, so he's the co-author of this paper. And then, indeed, this was due to Rabi flopping phenomena. Why? It's no longer just this simple periodicity, sinusoidal periodicity. This is, if you have two pulses, right? And when you have overlap, when you have one pulse, they interfere with the other pulse, then you will end up, like this is the case, is within that interference, you swing the thing, go all the way from this regime to that regime. So this is the case when your interference pulse ended up bring the operation of this qubit to this regime. That's why you see this dip instead of a simple sinusoidal. So, and that I would like to, so then you have the fitting. So this is the case that, okay, it's very simple block equation solution, but now this is, if you do this two pulse interference, then in this case, okay, this gyration factor is become very complicated. Don't try this, okay? Or maybe I can assign this as a homework for you to derive this. Then you will kill me, right? Say, just unfair. But I will tell you, I didn't derive this. My student Han Tun derived this. I couldn't derive it because this has never been done, and so he derived it, and it works very well. And that was the simulation, okay? Now, then there is another one, say, well, then what happened if you have detuning? Then we also see that indeed this interference pattern now become like that. Since I'm coming from Texas, so I have to show you something. You know, you have ever seen this thing called lasso? Okay, now we have lasso on the Bloch sphere. Okay, so this is the case when we have two-pulse interference. Then because of this detuning delta omega, this Bloch vector is now being driven in this kind of oscillation. And of course, this is also similar to what people in doing a superconductor qubit is called Ramsey interference. It's all determined by this delta omega. Okay, so, and I thought I will entertain you with Texas hospitality. Okay, now. Okay, so this is really the quantum coherent control of single quantum dot, but I never say it is single quantum emitter. There is a reason why I don't call it single quantum. I don't call it coherent control of quantum emitter. Yes, I am controlling this two state. But what I look at, the quantum emitter is really come from total emission at different energy. I'm only using the luminescence intensity to tell me what is the state here. I only look at how it projects back to the vertical axis. So one of the idea about behind this thing called quantum emitter, coherent controlling quantum emitter, is you want to be able to operate the matter qubit, which is your quantum dot. You want to be able to maintain it. You want to be able to then that this quantum information being carried out by the photon. So the photon has to be this quantum information carrier. Then it will go to the other quantum dot or the other quantum object. So in this case, you create an interface. So this is what people call quantum interface, quantum network. So it's very critical to be able to do that.